Good evening, everybody. Welcome to tonight's episode of the Astro Imaging channel. Tonight we have Niels Haagh, who is coming to us live from Denmark, so very early in the morning for him. We're glad that he's here. Before we get to his presentation, I want to real quick just go over what shows we've got coming up here. Oh, this has changed. Okay. There we go. Yeah, so we have Niels tonight. Next week is the Astro Imaging Channel workshop. So we've had a number of people, we put out the challenge to process Kevin Moorfield's NGC 2467, which is this gorgeous nebula down in Puppis. So not one that's normally accessible to us up here in the Northern Hemisphere. And we've got, I think, 4 people, possibly a 5th, I got to find out, who are going to come on and talk about how they've processed it, some tidbits on, not their entire processing chains, that would take a long time, but some tidbits on how they did something different and interesting with it for your consumption and learning. Then we have Sean Walker the following week, who's speaking for a team of people who've been doing this hydrogen alpha survey over the entire night sky. So that should be a pretty fascinating one as well. Followed by Tom Palmer talking about the super exciting NINA target scheduler, and then onward from there, but that's the next couple of weeks there. Yes, and so since we are live, then this gives an opportunity for you guys to ask questions live to our speaker. So make sure to put those questions into the chat and we will field them to our speaker. It's the great opportunity of the show being live that we get to do that. Yeah, so let's go ahead and get to that. So we have Niels tonight. He's been an amateur astronomer since the 1970s, back in the film days. He's a board member of the Copenhagen Astronomical Society, and he'll be talking about doing astrophotography on Altitude-Azimuth mounts. So Niels, take it away.
Thank you very much. Yes, thank you very much. I am very glad to be given the opportunity to tell you about LA's mount and astrophotography, as that is one of my passions. Almost everybody today uses a polar aligned mount or an equatorial mount when they take astrophotos, and I believe most of you do that too. But on many occasions, an alt-az mount can also be fast and simple, even faster and simpler to use. And in this presentation, I will look at when and why and how you can use an LA's mount for astrophotography. The agenda for today is that I will start with a very short presentation of who am I. Then I will go into the area of when it makes sense to use an LA's mount for astrophotography. Then going into a bit of why it is interesting to use an LA's mount, and I will make a comparison between LA's mounts and the more normal polar or equatorial mounts. And then in the how section, I will go into more details about how do you actually take a picture or take astrophotography with an LA's mount. And one of the important areas is looking at, for example, the settings for PhD 2 when you do guiding on an LA's mount. And finally, I will try to sum up and look at some examples of when it makes sense to use the LA's mount for astrophotography. Shortly about me, I became an amateur astronomer already when I was a teenager, and I was lucky to have a chance to go 4 months to Australia just after high school, where I stayed the technical manager of one of the big telescopes on Siding Spring Observatory. I stayed with his family for 4 months in the outback, very close to the observatory. And I had a great chance to image and observe the return of Halley's comet. And I also had many good visits at the observatory and saw all the telescopes close up. So that meant when I returned to Denmark after that, I decided to become a mechanical engineer. So I took a Bachelor of Science in Mechanical Engineering. On my hobby side, I've been doing astrophotography, well, since those days. So I've been going through all the steps of films and into all the electronic equipment that we have today. And finally, about 15 years ago, I founded the company Track the Stars, where we produce LA's telescope mounts for visual observations and for imaging. Okay, let's have a look at the next step here. When will it make sense to use an LS mount for astrophotography? Before I step into that, I would like just to set a little bit the scope of this presentation. I'll be talking about, you can say, the mount side of astrophotography. So it'll be mainly on how do you get your well-guided exposures. So we'll not be talking very much about cameras and focusing or filters and all the other things that we have to work with when we want to take a good astrophoto. It's the mount that's going to be the main subject for this presentation. And again, to set the scope a bit, we are going to talk about two types of mounts here. We have the typical polar aligned mount, where you set up the mount with one axis parallel to the rotation axis of the Earth. And when you do that, you will have a simple rotation around one axis will keep the object centered in the field of view. The other mount we'll talk about will be the LS mount, which we'll talk most about. And there you have, of course, the vertical azimuth axis and a horizontal altitude axis. So it's just set up on the location where you are and being vertical. And here is just a short presentation showing how the movement pattern of the two mounts typically are. If you look at a German equatorial mount here, you will see that it can track from east to west, rotating around one axis. And when it passes south, it performs the meridian flip. On the Azimuth mount, you have the movement where the telescope also tracks from east to west, but it rotates around two axes. The azimuth axis rotates clockwise to come from east to west, and the altitude axis raises the telescope until you reach south, and then lower it again to make the mount follow the objects over the sky. And just a few examples of the two telescope types of mounts here. Here you have some different equatorial mounts. I'm sure you know many of these. Skywatch EQ6, which is used by a lot of people. An astrophysics mount, 10 micron mount, plane wave, and a Schmidt-Cassegrain mount here. They are all set up here as polar aligned mounts. And on the other side here, we have a number of Altitude-Azimuth mounts. And if you look carefully at it, you can see some of them are the same. The 10 micron, the EQ6 can be set up both as polar aligned mount and as LS mount. And if you look at, for example, the plane wave here, it's actually a LS fork mount, but it can be placed on a wedge to be a polar aligned mount. And the same count for the Schmidt-Cassegrain, where you can see it's an LS mount, but can be placed on a wedge to get a polar aligned mount. So this is just to give you a picture of the different mount types. It's very important when we talk about this that we also remember to consider the quality. Traditionally, LS mount has always been considered as being visual mounts with less precise tracking capabilities. And when we want to use an LS mount for imaging, we need to demand the same quality as we do for an equatorial mount when we do that. So we have to look at similar quality products when we look at this. Okay, the traditional way to do astrophotography is always to use a polar aligned mount. It can be with a small telescope or it can be with big telescopes. But generally, amateur astronomers always use polar aligned mounts. Only the very biggest telescope, the professional ones, they use LS mount for astrophotography or for all their observations, of course. What I would like to look at today is that in many cases, it will be more convenient to use an LS mount for astrophotography instead of the traditional equatorial mount. And let's try and look at some examples of where that could be the case. This is just some examples, but I'll pick them out just to have something clear to discuss. If you're setting up to do astrophotography in real cold weather, where it's freezing cold outside, then it's great if you can stay inside as much as possible and control things from there. With an LS mount, you can set it up very fast. You can do it even in the daylight, and then you can start up everything remotely from indoors. You don't need to be out at the telescope after you have set it up, which is an advantage. And this can, of course, be used for astrophotography, but also people doing EAA would benefit from this in the very cold weather seasons. That's one example. Another example, which is very convenient when you live, for example, in the weather we have in Denmark, we have very few clear nights. So when we have a sudden unexpected clearing, it's nice to be able to get out very fast and get the best from the few hours where the sky is clear. And again, an LS mount can be set up very fast, so it's possible to be ready for some short observation session while the sky is clear. I'm sure some of you guys live in places around the world where the sky is clear and dark for a long extended period, and then this of course makes less sense. But if you live like me in a more unstable weather, this can be quite important. Another example is when you want to do daytime observations or in the twilight. It's very easy to align an LS mount at daytime. So to do solar observations, that could even be solar eclipse observations, or it could be that you want to observe some of the brighter planets during the daytime. And finally, an example could be you are out hunting a comet quite low in west just after sunset. Well, you don't need to use time to align the mount after the sun has set. You can simply get started as soon as it's possible to see the object. Finally, an issue about a situation about observatories. Perhaps you only have room to build a very small shed in your backyard for your telescope. And again here, when you look at an LS mount, well, the movement pattern means that it takes up less space in the observatory than an equatorial mount. So that can be an advantage in that situation. And to sum up, one of the real benefits generally is that with an LS mount, you don't have to make polar alignment. So that step is simply not part of the fun when you do astrophotography with an LS mount. So these were the 5 examples that I would like to look a bit more at. Then I'll move on to why we should use an LS mount in more details, and I'll try to make a comparison between LS mounts and polar aligned or equatorial mounts. In the process of preparing an observation night, the first step is to set up the equipment. And with the polar alignment, you typically need to do some kind of leveling, and you need to of the pier, and you need to adjust the pier also in the direction of north or south if you're on the southern hemisphere, to be able to make a good polar alignment. Whereas with the LS mount, you don't need to do any leveling or any direction pointing of the tripod or the pier. Then we have the polar alignment process. That will be the next step for a polar aligned mount. And you'll need to work your way through this process, either using a bit of old stylish, perhaps the finder scope, or a more modern solution to have some kind of polar alignment camera or some on-the-mount software that can help you to run through this process. But no matter what, even though there's a lot of tools to help you, you still have to do it. Where on the Altitude-Azimuth mount, there's no need to do any polar alignment. Then the next step would be to get the mount or the telescope aligned with the stars, and that can be done in the same way on both types of mount using an eyepiece, but generally it's some kind of plate solving or something like that, or the camera will make you able to align on one or more stars to get a good alignment of the mount. Then I have a slide here about eyepiece position. You know, eyepiece, that's the plug you use to keep dust out of your telescope when you remove the camera, I guess, at least for most of you people. But if you happen to sometimes look in the eyepiece, then you'll see that the movement pattern of the equatorial mount is so that the eyepiece position changes quite a lot. Even before the meridian flip, you have some angle change, and after the meridian flip, the eyepiece is actually turned upside down. Whereas on the LS mount, the eyepiece stays in a good position for all night long for doing the observations. Then we'll talk about the meridian flip, which is also acquainted with the German equatorial mount. And I'm sure you all know what a meridian flip is, but it will show up at just when you're passing the meridian in the middle of your imaging session. The telescope has to perform the meridian flip and going from one side of the meridian to the other. And when that happens, the telescope is turned upside down, and you have to kind of reframe and restart your guiding and imaging after the meridian flip has taken place. You could also say that if you have like a big mirror telescope, you could have the mirror shift in your mirror cell if you're unlucky, because you are turning the telescope 180 degrees upside down, so the mirror will move to the other side of the cell. Hopefully it shouldn't happen anything, but it's not an optimal situation. On the LS mount, on the other hand, the telescope can move from east to west without any kind of stopping its movement. You can say this is a bit the same as you can have on an equatorial fork mount, where you can also observe from east to west without any kind of disturbance. Then I have selected to look at the compactness in the observatory, or generally you can say it's compact, but if you have an observatory, it's nice to have a compact telescope. And if you look at these two telescopes here, you have the mirror telescope here on the equatorial mount, and sometimes the telescope will be on the east side of the polar axis here, meaning the whole diameter of the telescope will be on this side of the center of the dome, and sometimes when you observe the other part of the sky, it will be over here on the other side. So the space the telescope can take up in the observatory is all the way from this side and all the way to the other side of to where the counterweight axis is. Whereas if you have an LS mount like this planeway, well, it will be placed centrally in the observatory and will move in the same pattern in any direction. So the center of a telescope will always stay in the exact middle of the dome. Then we have to talk about field rotation, which is something that happens on all LA's mounts. And it is something that must be handled to be able to image with an LA's mount. And field rotation is not present when you use a polar aligned mount. And field rotation is something we will dig into now and look at in more details shortly. If we sum up these points here about the mounts, you can see how the list looks here, and I will move on right away to this list where I have picked out the most important points for when we do astrophotography. Of course, not needing to do the polar alignment process on the LS mount is a positive thing for the LS mount. Not having the meridian flip is a positive thing. And not having the field rotation on the polar aligned mount is a positive thing for the polar aligned mount. So this is kind of the most important things when we compare the two mounts for astrophotography. Now we're going to talk a bit more about field rotation and how that can be handled. Yeah, here is an example of or an explanation of what field rotation is. If you look at this graph here, the red square here is the image sensor of a telescope placed on an LS mount. And an LS mount, as it moves in a horizontal system, the sensor will always be parallel with the horizon. So it will never change its angle for the horizon. If you look now at the moon here and you see how the orbit of the moon getting up in east and moving over the sky and setting at west. If you look out at the moon in east, it will typically be tilted a bit to the left like this. When it's the half moon we look here. When we look at it, when it comes up to south, the terminator will be more or less vertical like this. And when it sets in west, it will be tilted a bit to the right. So that's the movement pattern, you can say, of all objects across the sky if you are looking towards south and just follow them, how they move across the sky. And if we take a picture in these three positions, as you can see right away, well, the moon will be a different angle on the sensor. And that is actually field rotation. So to be able to take pictures of an object being in these three positions and stack them on top of each other to one final image, then we need to do something to get rid of this field rotation. This field rotation is, just to put that into context also, the field rotation is changing speed in different parts of the sky. So it's not always just like when you're having the equatorial mount, you have the polar axis running at one speed. The field rotation is not the same all the time. So when you have to follow this, it has to move in different speeds. And actually, it also changes direction. When you look toward south, the field rotation will be clockwise. If you look toward north, it will be counterclockwise. And in east and west, that's where it changes the direction. So that's where the speed also gets very slow. And just to show you what happens if you, from the field rotation, if you take a long guided exposure on an LS mount with no derotation, you'll get a picture looking like this. It looks a bit like star trails around the pole star. But actually, the star in the center of this nice circular arcs, well, that's the guide star. The guide star is tracked, of course, precisely, and all the other stars will be seen as they rotate around the guide star. And how do we handle this situation with the field rotation? I'll just spend a little time, or just a few minutes, on the simple solution. If you are, especially if you are beginning in astrophotography, a newcomer there, then you can actually solve this problem by using short exposures. The field rotation is slow enough to allow something between 50 and 60 seconds exposures without having the field rotation visible in the individual subs. So if you are going out to image an object, well, you can take as many subs of 15 to 60 seconds as you like, and then afterwards align these and stack them as you would do normally with images taken with an equatorial, on an equatorial mount. The stacking software handles the rotation perfectly, so it will end up with a nice stacked image. The only thing is, if you do it for an extended period, of course, the edges of the image will not be covered on all the subs, so you'll have a limited field of view that will be perfectly lit. So for smaller targets, this is very good. For large targets, it's where you want to use the whole field of view. It's a little bit more problem, but it's a simple way to get started. And of course, also with these short exposure, you can often do it without any guiding or anything. So that's a very easy way to get started. And that's also why it's also perfect for doing electronic assisted astronomy. Very easy to set up and easy to get going. And I have just taken two examples of images here just to show what can be made like this. This is a galaxy in Andromeda, and it's with 10-second exposures, 840 of them. So it's a little bit more than 2 hours taken with my TIC refractor. And another image here, which is of course the Ring Nebula. And here it's a bit of almost lucky imaging, because it's 1 second exposures and 2,000 of those stacked together. Okay, but that's, you can say, is a principle for getting started fast, but of course not what we want to do in the long run, where we want to do good long subs to be able to go for fainter targets and better results. So we need to handle this field rotation. And the way to do that is to have a derotator unit connected to the telescope. And there are two kinds of derotators that can be used. One type is one that you install on the focuser of the telescope, and it will rotate the equipment you install on the telescope behind, you can say, the telescope, typically the camera and the guide setup. And the other solution is to use this device, which is a telescope rotator, which rotates the entire telescope and any guide telescope and everything on top of it. Let's look a little bit more at these two devices. If we look at the telescope rotator, then it's, as I said, just mentioned, rotates the entire optical tube assembly. This unit here has a dovetail at the bottom and a dovetail saddle on the top here. And it allows for a rotation of 30 degrees. This is a unit that we produce at Tracker Stars, and it's the only unit that exists, so nobody else is making a product like this. And it works for imaging through the telescope, but you can also use it for doing imaging with piggyback photo lens, or whatever you place on the OTA will track the stars correctly without any field rotation. And it also means that you can guide with a piggyback guider, or you can guide off axis. It gives perfect tracking for 1 to 2 hours, and then it must be rewound, because it's only have this limited angle of rotation. So you can do up to 2 hours imaging, then you rewind it and start again. The other solution, as I mentioned, is the camera rotator, and it's only for imaging through the telescope. And you will need to guide through the same telescope as you are imaging with and rotate the guider. So you need an off-axis guider placed behind the rotator. The camera rotator can, of course, rotate a full turn, which means you can track as long as you like, all night long, from east to west. And you can also use the same rotator for framing the target before you start taking the shots. Before I move on, I'll just mention also that this system here is especially well suited for fast system like if you have a RASA or a Hyperstar system where you can do very fast imaging, because in these systems you can't use a camera rotator, as you can't install that in front of the telescope. So for those kind of fast telescope, you can use this system. And often you can say 1 to 2 hours will give you a good bit of light with these very fast systems. Okay, that was a bit about why it makes sense to use an LS mount and this comparison between the two types of mounts. Then we'll move on and look at how to use an LS mount for astrophotography.
Niels,
Yeah.
I have a question. Can you comment on the precision of, say, a derotator or your tilt device? Because it's an extra degree of freedom and an extra bit of error introduced in addition to what you might ordinarily have.
Actually, I have a slide shortly where I will exactly look at the rotator and the necessary accuracy. So if we can wait for that, that'll be the best.
Sure. Any more questions from our crew? I don't see anything online.
I will come back to it in a very few slides. Then we'll look at the accuracy.
Okay, thank you.
Yeah. Okay. Okay, the equipment needed for this. Of course, we're starting. We need a good quality LS mount, and I've just called it astrophoto quality, just to put some term on it. But we need to be able to do a decent tracking and guiding to the accuracy needed to take a good picture, exactly as you would expect from an equatorial mount. And of course, we need to be able to have ASCOM control and guide input. Then it's very nice to have an electronic focuser, especially if you want to do things remotely from the PC. You'll need then the camera rotator, and I've written here we will want to have a resolution of more than 100,000 steps. So that's already a little bit about the accuracy needed, as there was a question about a short time ago. So about 100,000 steps per revolution is needed to be able to get a stable rotation and also have the off-axis guider working correctly. And that's the next device here. We need the off-axis guider with a guide camera, and it has to be installed behind the telescope, or sorry, the camera rotator. And of course, then we have the main imaging camera. And if you are using a monochrome camera, you will need to input the filter wheel somewhere in the image train where it will fit best. And now in this talking about this equipment, I know on this how to do this, I will mainly focus on the camera rotator. But you can say you could use the telescope rotator, and that will be installed up here under the telescope, and then the camera rotator would not be down here, but the rest would be the same setup. So this is the hardware, we can call it, devices that needed for doing the imaging. Then on the software side, we need some general astrophoto control software. I don't know what the right term for this is, but I'm sure you all use that today already for controlling your mount. It could be Nina or Sequence Generator Pro or some of the other software programs that I have mentioned here. So to control the camera, the filter wheel, the focuser, the rotator, everything, and to be able to make a sequence or a script that will take the pictures for you. You'll need that for doing the imaging, of course. Then something, especially for the LS mount, you need some software to make to run the camera rotator. As I mentioned earlier, when we talked about field rotation, the speed of the field rotation is not the same all over the sky. So we need a program to calculate the direction and speed of the camera rotator to be able to make a correct derotation of the field rotation. And some of the manufacturers of rotators, here I've mentioned Primoluculab, Pegasus, Falcon Rotator, and Optech, Planewave. They all do some software solutions that can make this LS derotation. One thing to mention about these software solutions is they do not know anything about the setup angle of the mount, which means they expect the mount to be set up perfectly vertical. So the tracking is based on that. So we can call it a true LS mount and not tilted in any direction. If you instead use like the camera rotator that we have for the Panther mount, then the software to control the rotator is in the mount by itself. So it's not an extra piece of software. The mount does it automatically. And it also handles the setup angle. So it means that no matter what angle the mount is set up, the software will calculate the correct derotation rate. So that's an advantage to have that possibility. But actually, we are at the moment working on a solution for our SCOM driver to make this field rotation value from the mount available for other camera rotators, so that the setup angle of the telescope mount can control the rotator instead of that you need to set it up precisely. So that will help the quick setup of the mount, which is actually one of the benefits that we are looking for when we use an LS mount for imaging. So that will be a future solution to have this in the SCOM driver.
Niels, I'm sorry to interrupt. There was a question I missed. What's the weight limitation of your telescope rotator?
Well, it's about 20 kilo for you can say a small OTA, meaning not too big diameter. If it's a big diameter OTA, then the number will be lower. So if you put on like a 10-inch Newtonian, then it'll be a good bit lower than the 20 kilo because of the torque you get from that distance up to the center of the telescope. But otherwise, it is 20 kilos.
Thank you.
Okay, we move on with the software needed to run this software photo setup, and that of course the guide software. And I have only looked at PhD2, so that's what I'm going to look more into today, and what I also suggest to use. But I believe other kind of guiders can be used too with the right settings. That was the equipment needed, hardware and software, and I will try to go through a step-by-step process of setting up and taking an image. First, of course, you need to build up the mount, telescope, and camera. And with the LS mount, there's no need to level anything or put any direction or anything on it. So you just build up the mount and install the telescope and balance it. And of course, connect all your equipment, camera, cables, and whatever as you usually do. And finally, you'll connect the power and the PC, so everything is connected. And then, if you want to do a remote alignment, for example, with a Panda mount, then you'll point the telescope somewhere up in the sky at 30-40 degrees altitude and just leave it there. And all this could be done in the daytime. And of course, you don't have any leveling or polar alignment, so you can actually, when you have set up the telescope, you can move inside, and then you can do the alignment of the mount via plate solve. So typically, you'll do a 2-star alignment, pointing at two, not stars, but just two different parts of the sky, some, I don't know, 60 degrees from each other. And then you do a plate solve in that area and input the position. And when you've done that on two different parts of the sky, then the mount is completely aligned. I believe this can be done on other LS mounts too, but I don't know all the different models, so you'll have to look into that depending on what kind of LS mount you have and then what is possible to do there. When the mount is aligned and running, then you can go into your control software where you can do the slew to the target, you can center it, you can rotate using the camera rotator to get the perfect field of view that you'd like to have. You can use plate solve to make a very precise centering, and of course you can perform your focusing so that everything is ready to run. Then you need to start the camera rotator with a rotating software. And one thing I have mentioned here, you need to be sure to have the correct latitude and longitude settings in the software running the rotator, because that is being used for calculating the field rotation speed. And I'm showing here the solution from Primaluzzo Lab called the Play software. I've been doing some tests together with them where we're using their Arco rotator, and they have just recently, or actually right now, they are updating the software to improved handling of the field rotation. So in there, you can select the object, and then the field rotation will start with the correct values for and speed for that object and that part of the sky. And then we are coming to the guiding, which is where the main difference in how to do things compared to the polar alignment mount shows up. You need to calibrate and start the guider. But before you do that, there are some settings that has to be set correctly in PhD2 to be able to guide the mount. First, you need to understand that both axles on the mount are tracking continuously, just like the RA axle on a polar aligned mount. So this means there are no backslash issues. The axles or the motors are never reversed. They're always running in one direction. You're just speeding them up or slowing them down. So backlash is no issue here. And also, there's no change in tracking direction, as I just mentioned. So that will, yeah, that's what I just mentioned. So it will be tracking in one direction. Then when you look at the settings, you have something called the guides algorithms. You need to be sure to have especially the declination axis set for this called hysteresis. Or at least you need to select one of the systems that you can use on the RA axis on an equatorial mount. So I suggest using hysteresis on both axes. If you have some of the other possible modes for declination, the guiding will not work. So, and you also need to set this here, the guide mode to auto, and not anything like locked north or locked south or anything. So these three settings, set them, and then the guiding will work with an LS mount. Some other settings to be aware of when you have when you start talking, we talk about your polar aligned mount, then you know that the guide in RA changes with the declination. If you have an object very close to the polar axis, the movement in RA will be very small when you do a guide command. Where if you are down very close to the equator, then the movement will be large. And it's exactly the same on an LS mount, but now we are not talking the declination of the object, we are talking the altitude. So if the object is close to the horizon, which is altitude 0, then you'll have a big movement of the azimuth axis when you do a guide command. But if you're getting very high in the sky, then you'll have a small movement. And this has to be handled to get good guiding. The first thing always to do is to disable this here, declination compensation. If you have that enabled, then the PhD will use the declination to set the guide commands, and that will not work on an LS mount. So be sure to untick this point. And when we are at it, you should also be sure that you don't have anything reversing the output after a meridian flip. As the mount never flips, the commands will always be in the same direction. Then getting back to handling this changing azimuth guide, the first option is that you calibrate at the same altitude or approximately the same altitude as the target. And then you need to recalibrate at some interval. That could be every 1 to 2 hours. Typically, the guider will run very smoothly for quite a good period before the change in altitude will influence on the guiding. And this recalibrating every 1 to 2 hours can be input to your script. For example, if you're using Nina, you can ask it to make this recalibration automatically. Another option is to use the more manual version. In PhD, you can select what they call auxiliary mount. You can select something called ask for coordinates. That means when you push start on your guider, then you will get this small screen popping up asking for the declination. And in this point, in this field, you should now input not the declination, but the altitude, which you can typically get from the software, either the software you have on your PC, or you can see it on the mount handpad. So if you input the altitude at this point, then the guiding will be correct for that altitude. So that means you can calibrate low in the sky where you get the best calibration, and then you can input this number, input the altitude here, and get good guiding at all altitudes. Okay, also about this change in altitude and the guiding, we have just recently made a new ASCOM driver for the Panther mount where we have introduced this compensation in the driver. That means if you tick this altitude compensation on, then the ASCOM driver will compensate the guiding for the altitude automatically without doing anything in PhD. So that will solve the problem, and you can guide for extended periods and over changing altitudes without any problems. Okay, next things in PhD is that we have also the camera rotator. When that's rotating, doing the derotation following the sky, then the guide camera sitting here after the rotator will rotate. And that means that the alignment, or sorry, the calibration you have made in PhD will change over time. And at some point, it will not guide correctly anymore. And to be able to handle that, there are two options. The first option is the same as you could do for the altitude, is simply to have your imaging sequence recalibrate PhD every 1 to 2 hours. That recalibration will solve both the rotation issue and the altitude compensation. The other option, option 2 here, is to connect the rotator to PhD2, and then PhD2 will automatically make the compensation. And you can do that here when you connect the equipment. You can connect your rotator to PhD2 to get this compensation. And that's it. Having everything set up here, and of course, all the steps on the guider is something you only need to do once, then it's ready every time. But except from that, these are the steps you have to go through, and then you can just start taking the subs. I am perhaps missing a sub concerning, missing a slide concerning the field rotation position I had the question about before. So I'll just have a quick look where that is. Just give me 1 second here. Okay, here it is. Somehow that has been hidden. Derotation accuracy demands, which there was a question about earlier, and of course it's quite important to talk about here. If you look at your normal guiding, and in this example I've made here, you have a telescope with a focal length of 1 meter or 1,000 millimeters. If you want to guide that with, as an example here, 1 arcsecond accuracy, then you'll get a certain error on the sensor, or the star will move a certain distance from the center if it moves 1 arcsecond here. And that distance, if we calculate that, is 4.8 micron. So that's, you can say, the size of the star if the movement is, the guiding is 1 arcsecond. If we then look on the derotation accuracy, then the first thing to understand is that the only thing that has influence on this is the sensor size. The focal length of the telescope has no influence on the needed accuracy for the derotation, because it's the sensor size that decides this. You have to look at it in this way. The sensor rotates around the center point, of course, and at a certain rotation angle, the error you will have out here at the very corner, which is the worst place, will be, for example, these 4.8 microns. If we insert the 4.8 micron out here, so we want the rotator to rotate the sensor with a precision which is similar to the 4.8 micron we have over here. Then the actually angle distance we have here is only the diagonal of the sensor, which is 21 millimeter here, which this is a full frame sensor. So the needed accuracy for the derotation is 46 arcseconds. So it's a lot smaller. Actually, it's 50 times smaller than the mount axis demand. So you can say if your main mount needs to be able to track the object with 1 arcsecond accuracy or half an arcsecond accuracy, of course including the guiding, then the demand for the rotator is 50 times smaller. And typically that can be handled right away with the rotator. I hope that explained the question that was there. earlier. And then I will jump back to where I was in the presentation. I apologize for this confusion.
So what you're saying is basically any decent derotator is not going to affect the accuracy of your captures.
I'm saying yes, that's what I'm saying. But I will say, as I also mentioned on one of the other slides, you need to have a fairly high step accuracy. Some rotators do not have enough steps because they are mainly made for framing targets. So where the accuracy is needed, it's not very big. So you need to have enough steps or small enough steps to be able to get a smooth tracking, especially also for the guiding, because the guide star is being, or the off-axis guider is being rotated too. I have tried to test with rotator with very few steps, and what happens is that when you're guiding, every time the rotator makes a step, the guide star moves a little bit away from the position. You can simply see the steps on the guiding, but on the steps on the rotators with enough steps, you don't see anything at all. The guiding is perfect as with any other mount.
Another question that came up, do you have any comments about the taking of flats?
I can, yeah, we can. I have not made any slides on that, but we can discuss that too, and we can do that now. That's fine. You can say, of course, you'll have the the camera are rotating relative to the telescope. I think I will show this slide here.
So if the camera is rotating relative to the telescope and you have a cigarette burn or something in the telescope, then that is going to rotate, correct?
Typically, yeah, things coming from the telescope. But my experience, and I believe that that's fairly correct, but that most of the things you see of defects you're seeing, like donuts or all kind of things, dust donut, most of these things are coming from the back end of the image trains. It's something sitting on your filters or somewhere in this part of the telescope. So in my experience, the flats are quite good, even though you rotate the camera. But that's of course something you must experience yourself. But generally, I don't see it as a problem.
Are there any other images, any other issues that you see with calibrating using an alt-az mount and a derotator?
No, the only issue you can say will be the situation of having the rotated flat, which I believe is a very small problem. Actually, I've been trying to find out what they're doing on the professional telescope regarding this, because they have the same situation where they are rotating their instruments, and from doing those kind of measurements, they need very precise flats sometimes. But actually, I'm not aware how exactly it's done on a telescope like that. So I have no other comments to calibration, except that in my experience, it's not a problem.
If there are any more questions, I think we're kind of getting towards the end of Niels' presentation. So if you have any other comments out on YouTube land, please put them in.
I have a few final slides, which only
okay. Please go ahead.
Yeah, just a second. Actually, it's just summing up on the 5 teasers, or whatever we should call them, that examples that I put up in the beginning. First thing was, well, I said that it made good sense to use this in cold weather. Now you have seen through the presentation that the things that give this example sense is that you don't need to level the pier, you don't need to do polar alignment, and you can do everything remotely. So that's where the LS mount is nice in cold weather compared to the equatorial mount, because on any equatorial mount, you need to go outside and adjust the polar alignment knobs. Even though you can do a lot of the polar alignment from software, you still need to be at the telescope and turning the knobs until you have the correct polar alignment. The next one was the sudden clearing. I won't say much about that now because it's again related to no leveling of the tripod up here, no need to use time for polar alignment, and a quick 2-star alignment, so you can start up very fast as soon as the weather clears. And daytime observations, it's possible when you've set up an LS mount, you can align on the sun. You can use it as one object just to get a first alignment where it will track the sun. The accuracy will depend on how the mount is set up. If it's leveled, so then it will track the sun quite nicely just from one alignment on the sun. But otherwise, you can simply wait some minutes. I don't know, it could be 30 minutes, it could be less. And then as the sun starts to move a little bit out of the field of view, you recenter it and set the sun as aligned object 2, and then you'll have perfect tracking of the sun. And of course, you also have the possibility to slew to a planet or a bright star in the daytime and do an alignment on that. So you can get a quite good alignment completely during the daytime, also making you ready to do observation as soon as the first darkness shows up. And the small observatory, I just have this small sketch demonstrating a little bit the space taking up. We have already talked about that earlier, so it's just to show that the equatorial mount, when it swings around, it will move from side to side, taking up a certain space in the observatory, where a top-loaded LS mount will do a very narrow envelope in the observatory, so there's more room to be around the telescope. That was actually what I wanted to say. I'll just show you. I have a small blog called telescopemount.org, where I have written some articles about different aspects of LS mounts and LS astrophotography, and some of the things I've shown here can be seen there if that should be interesting. And then, of course, just shortly, the mounts that we produce at Track the Stars, we have 2 mounts. We have the Panther mount, which is a small transportable mount. And then we have a big mount called Mammoth, which is to be used in an observatory for larger telescopes. That was it. I hope you enjoyed the presentation. If you have any questions, now's the time.
Yeah, I see that there's a discussion going on over at YouTube, and it's kind of brought up a question. Apparently, if you have a reflecting telescope with vanes, that the spikes will rotate, even if you have the derotator. Is that correct? Because you're rotating the camera, but the vanes are staying in the same position.
Yes.
So your spikes will rotate.
That is correct. Yes, your spikes will rotate to different positions. Yeah, I have actually mainly imaged with telescope, but because I expected perhaps somebody would ask this, I just let's see where it was. No, I don't know. I looked at some examples, but I can tell you, it's correct that the spikes will rotate, but actually what happens is they will disappear on the final image because they are being on so many different subs. So when you stack them, they will disappear. So you will have no spikes on your image. I wouldn't say what happens if you have a very bright star in the image, but the smaller spikes on most stars, they will simply disappear due to the stacking process.
It's really interesting.
So I wonder if the spikes will produce a larger halo around the star, since the spikes are
let me
brighter
show you.
towards the center of the star than they are, out at the
I
extremities.
found actually, just let me show you this here. This is a picture, you can actually read my comments here on it. It's a picture from Astro, which is taken with a plan wave CDK 700 in the LS configuration. So that's taken with a D-rotator. So I can't say anything except on this one, I don't see a big haze from that coming up. But
Yeah, I
it's,
guess that I'll just get rejected. That's interesting.
sorry?
Yeah, I guess pretty much the whole spike is going to get rejected. I think with that, if you have enough, if you have a lot of rotation, like you've done this over a whole night or many nights or something, rejection would pretty much eliminate the spikes. It looks like.
Yeah, it's interesting that you bring up plane wave, because they recommend their D-rotator and an alt-az configuration of their L mount. But this is the 700.
Yes. Yeah, it is. I don't know if you can read. I don't have the link here. If you can read there's an Astro link here.
Good gorgeous
looks
picture, by the way.
Yeah, Southern Hemisphere.
Yeah,
nice to have a big telescope.
It's from a remote telescope in Chile.
Nice.
Yeah.
Beautiful image. As long as we're putting it up, who's credited with this?
It's I had to tell that. Well, let's give me just a second. It's just give me a second.
If we're putting up that person's image or group.
Yeah, I'm aware of that.
Credit.
Yes, I should do that. Actually, I placed the link here, but I should put the credit here. Just give me a second.
If you put it in the chat, we can put it over on YouTube.
Now, Niels, this was taken with a rotator or D-rotator and a tube with spider vanes, right?
It's the plane wave, right?
Yeah.
There, right.
Yeah.
The
Okay, well, there's an answer to the question right there.
Yeah.
How long were the exposures each on these?
Why don't we, if you put up the link, then
just give me a second here.
Sure.
I'll just try and.
I'm not sure if that's an I or a 1, but neither one is working. But yeah, maybe just I'm not typing it in right.
Are you doing it, Molly?
Well, I was trying to go find the site, but I tried it with both an I and a. Oh, you know what? Maybe it's an L. Let me try that. There we go. Yeah, I got it. It's gmadcat is the username. I'll put it in the chat here.
Yeah, put it in the chat. I mean, we're putting that person's. I was going to say his image, but I don't want to be. It could be not a him. It could be a her.
Okay, there we go.
Cool. If you're done, you can stop sharing now, Niels.
Yeah, I'll do that. I'll do that.
Yeah, great presentation. I think it causes all of us to think a little bit, since we got our hands over our ears, then we have to do German equatorial. We can't think of alt-az, but this has got us all thinking a little bit, I'm sure.
Yeah.
Okay.
Yeah, there's some advantages there, and yeah, that is interesting.
It makes me think, should I really have set up my 520-inch plane wave?
Maybe you want the diffraction spikes, because then it looks.
I would say you can say if you have like a permanent installation, as you have like with a big telescope on a permanent remote setup, then the disadvantage of the equatorial mount is less, because you don't need to set it up, you don't need to polar alignment more than once. So a lot of the benefit for the LS mounts come from is extra when you do setting up every time for your session. But of course, the the meridian flip is of course always visible unless you have it on a fork mount. Then you of course have free from east to west observation even with a polar line mount.
Well, I had to get a 2,500 pound offset here. It takes up more space, and I needed a wedge, all of which was expensive one way or another. So,
Good point.
and had I done it after your presentation, it would have been something to think about. But
Okay.
now I got spikes.
Yeah, this is good. And I use I'm planning on using my single fork arm alt-az mount for like the solar eclipse, because then I don't have to polar line it, which is great for the solar eclipse. I use that for outreach events because then I can be set up during twilight. A lot of advantages there for sure. Eric, do we have any other questions on YouTube?
I don't see any. Sometimes they sneak in here at the last minute, but I don't see any.
Anybody else here got any more questions or remarks in the room?
Niels, after we end this show, you're welcome to stay with us. We have a little gossipy chat afterwards.
Or you can go to bed.
Or you can, go. Actually, it may be
No, it's fine.
where
Now I'm completely
too
awake
late.
now.
You're wound up. There's no way to go back to sleep.
Exactly.
Well, we thank you for your dedication of coming on here when it's really late for you. We have a difficult time getting European speakers for this reason, and we're glad you're able to join us live for sure. Actually,
if you can think of anyone in your part of the world that we might be interested in hearing from, please send along a name. We're always trying to recruit new people, and in that part of the world, we really don't have a lot of speakers. So, and I'm sure you have some very fine astrophotographers. So, if you're someone you'd like to suggest, and your experience wasn't
I'll
too
think
horrible,
about it.
please send them along.
I'll do that.
Appreciate it.
Great. Well, all right. I think that's about all we've got for tonight. So we'll go ahead and sign off, and have a good night, everybody.
Bye. Hope this. I'll be sure to come next week. We're going to have some
Yes, come next
great
week.
image. Come next week. Good night, everyone.